If a plane wave is traveling in a vacuum, a lossless media, it has some special properties that we can use to simplify calculations. And so let's just consider a plane wave that's traveling in a vacuum. And what's special about a vacuum? Well, what's special about a vacuum is that there's no charge in a perfect vacuum because there's nothing in the vacuum. So that the total, if I were to just sum up all the charge within the volume that the plane wave is traveling in, there is no charge. So we just say that's the charge-free condition. And the other thing about a vacuum is it doesn't conduct electricity, so conductivity is also equal to 0. So these are the two properties of a lossless medium, like a vacuum, which will allow us to simplify plane wave propagation. So let's start by applying these assumptions to the fact that gamma is equal to the square root of j omega magnetic permeability times conductivity plus j omega electric permittivity. What is going to happen with these simplifying assumptions here is that sigma, the conductivity, is going to drop out, and so this is going to reduce down to j squared omega squared mu times epsilon. And we can pull the j omega out front, mu epsilon. So what that shows us is that if there is no conductivity in a medium like a vacuum, alpha is equal to 0 and beta is equal to omega square root of mu epsilon. So we get some simplifying assumptions for lossless media, and the great thing is that, well, it's a vacuum, it has no conductivity. That simplifying assumption alone shows us that the attenuation constant is 0 Nepers per meter, which we would expect for a lossless situation. We know from our discussion of wave propagation that the propagation velocity of a wave is equal to angular frequency divided by wave number, and so here I've got omega divided by omega mu epsilon, which is equal to 1 over the square root of mu times epsilon. So this is equal to the speed of light divided by the square root of the relative electric permittivity for lossless media. That's the propagation velocity in meters per second. Finally, we can use our assumptions here to evaluate the condition for intrinsic impedance. Remember, eta, intrinsic impedance in ohms, is equal to the square root of j omega mu over sigma plus j omega epsilon. What's going to happen here is sigma goes to 0, and so we get j omega mu over j omega epsilon. The j omegas therefore cancel, and the intrinsic impedance of a lossless material is mu over epsilon. We could rewrite that as equal to mu 0, mu relative over epsilon 0, epsilon relative. It's a little messy, where that's the intrinsic permeability of free space, 4 pi times 10 to the minus 7th henries per meter, and that's the electric permittivity of free space, 8.854 times 10 to the minus 12th farads per meter. And so we can separate these two out, and we get mu 0 over epsilon 0 times mu relative over epsilon relative. And often this is written as the intrinsic impedance of a material, eta, is equal to the relative magnetic permeability divided by the electric permittivity. Take the root of that and then multiply it by this term eta sub naught, or eta 0, and we're just saying that eta 0 is equal to the square root of mu 0 over epsilon 0. And if we do that math, we get 4 pi times 10 to the minus 7th henries per meter, 8.854 4 times 10 to the minus 12 farads per meter. We do that math and you get 120 pi ohms. And what this tells us is that a plane wave traveling in a lossless media is going to see an impedance, just like a voltage or current wave traveling in a conductor sees an intrinsic impedance or a characteristic impedance. So what that allows us to do is perform some simplifications for writing traveling wave equations for the electric and the magnetic fields. And real simply, we can just say that in a lossless medium, H bar plus is equal to E bar plus divided by N0, and H bar minus is equal to minus E bar minus over N0. So these calculations give us a nice way to relate magnetic field and electric field strength for a plane wave as it travels through a lossless medium.